Today we are going to see the time response giving a particular transfer function, and we're going to learn also the influence of the zeros and the poles, as we call them, from the transfer functions and how they relate to the response of the system. On the screen you see transfer function and the location of the zeros and the poles of that transfer function. And what we're going to do is to study how that location influences the response of the system. Okay, so let's have a little bit more spacing here, and so that we can discuss this in more detail. You see, here's the transfer function. Okay, you have a numerator of the transfer function, you have the denominator of the transfer function. From now on, any root of the denominator is called pole. Okay, that's something we have to remember all the time from now on. Any root of the numerator is called poles. Zeros. Okay, any root of the denominator are the poles. Any root of the numerator are the zeros. So you see, if you have s plus 5 and you set this to 0, s obviously is minus 5, right? That minus 5 is placed right here. This is the plane, the s-plane in here, where we have the imaginary axis, and then we have the real axis over here. This is, we are plotting complex numbers, right? So in here, you can say this is the transfer function, and if 1 over s multiplies this transfer function, then you have another pole, because it's 1 over s. You know, if 1 over s is 0, right? So you have one pole here, you see, and you have 1 0 here at minus 2, and then you have one pole at minus 5. That is what you have in here. So the response, I mean the output, is going to be the combination of these three factors. That's what C of S is. Okay, so it's like this is the first 1 over S, and then if you do this multiplication, you can reduce it to its fraction like this. See? And what we are going to see is that when the system responds of this transfer function, the system is going to have a forced response part and a natural response, but it's going to be like an oscillating response. So depending on the values of what we have, although in this case with the poles on the real axis, this is not going to oscillate very much. So there you have, this is in general, if you have this plane and you have in here a pole, it means that the response of the system is of this type. Okay? Mathematically of this type. If you have the transfer function in this form, you only have one pole, and this is called first order system, and this is the pole right here. Okay, if you have this response of the system for a first order system, you will see a rise in here up until it reaches a steady state condition. So important to recognize in this response are several properties and points, you may say, of the response, which we should we should look into it. If you go about 60%, 63% of the final value at this time, this timing here, this interval is called the time constant. And if you plot or examine the curve right there at several intervals of the time constant, you will have points on the curve like that to study. Like here, it would be to the steady state response. So and the initial slope of the curve here is 1 over the time constant, that would be A. And so so we have the transient response and a steady state response, which would be the maximum value that it reaches. If you have a step input, this would be the response like that, where is the time, and then it would be the amplitude here. If you have this situation like this, you have these transfer functions are typical of this response. So for example, here, if you have this transfer function, you have 2 poles in here, and then you will obtain this kind of response. If you have this transfer function in here, you will get this response. If you have this one, you will get this. If you have, so the conclusion of this picture really is, depending on what these numbers are, the system will behave differently. Okay, so we would need to see where the location of these poles are on the S-plane, and then we will see exactly what the response is. So what I would like to do is we can take one of these, go to MATLAB, and then do the test so that we can see, in fact, verify what I'm telling you. The message, however, is exactly the same regardless of the transfer function. What I'm saying is, depending on what poles we have in here and what zeros we have in here, we will have a typical response like this. So as you go along and you become more proficient and practicing in this field, by looking at the transfer function and seeing how it's configured and what the poles are, you will be able to predict what the system is going to do. That's the point in this whole thing. So let's just go to MATLAB and do that test, okay? So here's the MATLAB. Okay, at the MATLAB prompt, we are going to describe that transfer function. So you see the transfer function has a numerator and it has a denominator. So we are going to say that the numerator of the transfer function is equal to you just have a 9 in there, right? So that is the numerator. And then the denominator of this transfer function is going to be equal to a polynomial in there, where you have the x squared has coefficient 1, the s has coefficient 9, and the constant term is 9. And you say, okay, that's the other polynomial in here. And then now we're going to define what the transfer function is. So we call it g is equal to transfer function of the numerator and then the denominator. And then you see what we just got? This transfer function here is exactly the same as we have over here. So in order to do this, to verify this, we're going to say step of the function, transfer function g, and you see we get the output, and that's exactly like this. Okay, the point being that by knowing this setup of the transfer function with two poles on the real axis, I can predict that the system is going to do this. And so what I would like to do is I would like to try another one, which we'll find it a little more interesting on the slide over here. Let's see which one is more interesting. I would say this one, the next one. In here, by tweaking those numbers, you see this has this kind of roots. But if instead of a 9 we have a 2, the roots are complex numbers. They have a real part and an imaginary part. And when you have this kind of roots placed here, you're going to get this answer. So what do we have to do to go from this example to this? Just basically change the denominator, right? So what I would do is, let me see if we can put it up. No, we cannot put it up. I will just have to move it. I just need to put a 2 in the denominator. So what I would do is, do you see this command in here, right here, this one? Instead of a 9, I am going to put a 2. Yeah? And click on return. And then I would have to redo the definition now with the new, which would be g is transfer function of the numerator and the denominator, and now we have the transfer function that we have on the back right here with the 2. We have it right here. And if I do the test for that, I will get this response. Do you see what I'm trying to say right now? And that's exactly what this is, what you have right in front of you with the software. So to drive my point, and perhaps in solid basis, what I'm trying to tell you now is that if we know how those poles are placed on the complex plane, we could predict the response of a system. That's the point. Okay? So, and of course the zeros have something to do with it, but really the what controls this, the main control is in the denominator. So what we are going to do here is we say, okay, for a moment let's do away with MATLAB. If you have this kind right here, let's say you don't have this term in here. Do you see what has happened here? Is you have the poles now on the imaginary axis. So we suppress the second, the second term. I think, but do you notice now that the system has become all oscillatory? What I'm going to do deliberately is to bring the poles on the right hand side, and you'll see what happens. I am going to suppress this and then just make it a 0 in there, and then see what this does. See if we get this. Okay, so let's go back to our MATLAB prompting here, and do you see the definition of the denominator is what we're after right here. I would say the denominator now, it is equal to what did we do? See, there it is. If I put this as 0 right here, I have created that situation. And if I say g is equal to the numerator, and denominator, what happened here? My syntax is not right. I need to tell it what we're doing. See right there, this transfer function that you see down here, yeah, right here, this one is what you have in here. Let's do the test. Step of G, and then let's see what happens. Oh, where is my plotting here? Okay. Step we have this step response, which is, you know, many oscillations in here, but in here I am going to venture and say, instead of the denominator being a 0, I am going to remember it was 2 before. I deliberately going to make it a -2. Yeah, and with that I define the transfer function. G again is going to be a transfer function of the numerator and the denominator. Yeah, define it as -2. And if I do this step of G, by the way, let me see if I don't have, we need to close this to see it. Let's see what's going to happen. This is interesting. Do you see what happened? It went in here, and at 0.25 it blew up. Do you see? So I think it's safe to say, when you have roots on the right hand side, or one of those coefficients on the denominator is negative, you could see that you are either you made some mistake on the derivation of the transfer function, or the system is messed up, because it will actually catastrophically fail. It will produce a response that, instead of damping vibration or behaving normally, oscillating and then stopping, it would actually increase the value of the response, and it is no good. So I think you see the message here that, again, I'm trying to give you, is that manipulating those coefficients on the denominator becomes crucial in sync control systems. Now that you know the bond graph technique, and that bond graphs can produce transfer functions in symbolic form, you could see the importance of that, because if you produce a transfer function in symbolic form, you know what physical parameters make up each coefficient. And you could say, well, if I needed to be higher, I would change either stiffness or a damping or whatever, you see, or decrease, depending on whatever the case is. So having transfer functions in symbolic form in terms of the physical parameters is a very useful tool to be able to make the system do whatever you want. Okay, I think I made my point, and so we are going to continue with the presentation in here with different properties of the response. Like you could say, when you have this kind of a response, is a combination of an exponential decay and also of an oscillation. So this is sinusoidal oscillation generated by a pair of complex pole pair. So a In other words, this kind of roots. So be able to recognize this. I remember in the, just to perhaps a personal story, when I was doing the PhD qualifying exam, they asked me about this, because you see, it is such a fundamental principle that is a must to know what the roots do to the response. So this is a simple concept, but it's something you really need to know. Okay, so here we go. So we could test this. This would be a different transfer function. If you test with, for example, this is the damping coefficient, right? And if you increase the damping or decrease, you will be more damping or less damping. So in here, you could study a system that is not damped, oscillates all the time, like we saw. You could study one that is critically damped, and one that is, it becomes over damped as we increase the value of the damping coefficient, or critically damped as it's just on the borderline. This is a more appreciation of what we just said. I think it's worth looking at. If you have a second order system, like obviously this is, you see, because it has this square. If you have this response, if you have it in here, you will get this. If the poles are imaginary, you will get this. This little constant is called the damping ratio, and it is the value of the damping of the system to the critical damp, meaning at the point where that damping becomes zero, right? So in here you have, if you have it between 0 and 1, you will obtain the poles like this. If it is 1, they would be like this. So you will get this response. And if you have bigger than 1, what you are doing, instead of moving the roots into this area, you are moving them to the left. Totally over-damped system. So this way you can see by the location of the poles the exact response you're going to get. Let's take a look at some other systems in here. Now, what would we have? What influence would it have if you change the numerator? Let's say like this have 12 like in here, and you have a 20 over here, or you make a change like this. It's all what we will obtain is this kind of things. You will have, see, the damping ratio would be 0.8, 0.6, 0.2, 0.1, and so the point being is that you can tweak the way the response will be by changing those numbers. That's the whole idea here. And in here you have a more detailed analysis of what I told you about decomposing the signal, on the maximum value, and how it would oscillate until C final is the so-called steady state response. So I would like to ask you to read this, please, in chapter 4 to reinforce what I'm telling you. I think you will be glad you did, because these are basic things that you must know, because what is coming later is I am going to ask you to modify the transfer function to obtain a certain damping ratio or to place the poles on a certain place, and that's why you need to go over that. Right? This is again the overshoot is the amount that goes over the value and be with respect to the steady state response. These are several experiments in here of changing the damping ratio and then looking at the rise time. You could do different things, but this picture that you have in here, you must have it in your mind. This one, forever and ever, should be engraved in your mind, because it is a generalized statement of the basic definition. Like, if these are the roots right here, complex roots, the distance between the origin to that root, this is the natural frequency of the system. And also the damping ratio is defined as psi times the natural frequency, which would be this value right here. Okay, and this would be the imaginary part, omega n square root of 1 minus the damping ratio in square. So this is also this part, this would be the damped frequency. So this is the natural frequency, this would be the damped frequency. So that's why this is important for you to remember. Okay, here we can play around with several definitions on the complex plane. This would be if you have a certain percentage overshoot, you would be following this line or this other line. Again, it's about the same thing. Where are those poles? And depending on where they are, the system does different things, you see? Okay. Let's examine this. For example, if the poles are here on the 1, follow the 1, you will get this answer. If you move them to 2, you will get this answer. And if you move them to 3, you will get this answer. So the envelope is the same, but obviously if you are going up, do you see the frequency increases? And remember, this was the value of the damped frequency. So the more the bigger this number is, you're gonna get the smaller oscillations. Okay. Look at B. In this case, you instead of moving the poles up, you're gonna move them to the left, but keep the value of the damping in here, and you move them to the left in here. The frequency is the same, but look at the response. So if you move the poles to the left, the system becomes slower. Wait a second. The system becomes faster, and then if you do the one of if you move it over here, then the system becomes slower. See here? Now, if you move it on a diagonal like that, you take the same overshoot, but do you see the frequency goes higher? as you go left. Same thing here, the frequency will go higher. I mean so we have it in 1, 2, and 3. System. See, do you see, closer to the axis the system is slower. Farther from the axis, system is faster. That's another thing that you need to remember from this discussion today. Again, another view of the same thing about the location of the poles, and this on the S-plane with the response of that example. Here are some examples that you find in chapter 4. This is the kind of thing that not on this, on a coming quiz on this topic, I will tell you, this is the system, find the transfer function and modify the poles and the zeros a certain way to make the system do that. If you have them in here, you see, this is what you will see. If you have those two and this, then you will you could modify to try case 1, or if you move this one to the left, try case 2. Do you see case 1 does this, but case 2 is faster, see here. Or case 3, if you move them over here. So I think over and over you are seeing with many of this how the response is. If I were you, you should go to MATLAB and modify those coefficients to see this kind of response, just so that you get convinced that in fact by doing this you could make it do what you want. See, different kind of response, slower, faster, higher, overshoot. There's another one, for example, the effect of adding a 0 to a 2-pole system, because the numerator also, it's important. So if you have a 0 at and here, you'll get this answer. You get the 0 at -10, you'll get the black one. 0 at -5, you'll get the blue, and 0 at -3, you'll get this. So this increases the overshoot if you increase the 0 value. Okay, this is different system to try, but the message is the same. What changes can we do? Something like this is what you see. You could see it just as a matter of review here. You already know how to obtain the transfer function between the output and the input in here by using this operational amplifier. Same thing over here. Just to do a change like in this step response with different changes. Finally, for example, if you have a transfer function, now that we are in this idea of modifying things, you have this transfer function like this, and then you could actually do something else outside the transfer function. Here's the idea here. You see, this is your transfer function here, and then we're going to do something. We're going to increase and put another block in here, which in fact is the controller in this case. And instead of having this response, this without saturation, without this block, you're gonna have it like this. What's the point over here? The point here is that by adding other blocks to the transfer function, we are modifying the system. Those so-called other blocks that I am mentioning right now are the control systems. But so you see how easily we are going from knowing a transfer function of a physical system to a physical system with control. So what I would say in the future lectures is that if we add a type of controls, we definitely will affect the output. And that's exactly what control systems do. In here you can see the if you, instead of the one that you put in here, we added this other two, depending, we're tweaking this. And we will go from this one to the blue. Or if we want to make it do this, some backlash in here, different transfer functions in here. For example, this integration block damps the oscillations. The integration block makes corrects the state error, but produce the oscillations here. Excuse me. But if we put the saturation, we'll make it do this. See? So there are ways to change all this. Your book has this kind of an example in there, and you can do several things in here. I would close this by showing you that if you have the transfer function of the vehicle in here, you can put this, you can do a feedback sensing, you could add this other, and in the modified completely the output. And that's the whole objective of transfer function, of control systems, is to modify the original response of the system to the one that we would like to have. So let's stop now.